Hello. We have finished two of the layers, the application layer and the transport layer. Now we're on the third layer, the internet layer. Just to remind you, the application layer took a program at one place, such as an email client, to a program at a different place, or the same, such as an email server. They were program to program. The transport layer didn't worry about the programs. It worried about the source that was had one program and the destination that had the other one. So it was the job when it got to the destination, the socket would figure out, when the transport layer sent it up to the application layer, that would be figured out there. Now, the network layer, it's been called the hinge of the whole system. The network layer is the first layer we've looked at that cares about the intermediate computers along the route from one place to another. Its job is very simple. It is supposed to get what it calls a datagram, which basically means the packet it received from above, from the transport layer, with a header that it puts on it. It has to get it from here to its neighbor. One hop. That's its first job. Get it from itself to one neighbor. But now there's a little more than that. It has to somehow figure out which neighbor. It has to take an input line and determine which output line is supposed to send this message on, which means it has to compute a route from the source to the destination. We build the route first within our own system. We call that an autonomous system to have a big name for it. It could be a LAN, could be a group of LANs. Each AS has a node which connects to the rest of the internet. If we are sending a message within our AS, we don't have to worry about the routing it outside. If we have to send it outside, what we have to do is figure out how to get the message to wherever the node is that connects to the outside world. So the first step is internal. How do we take a message from where we are to the node that connects to the rest of the world? Now that's going to be one kind of algorithm. Then the nodes that connect to one another that form the spine or the backbone or whatever of the internet, they're going to do a separate algorithm. They're going to say, how do I get it from this autonomous system to the autonomous system of the destination? So that's all they're going to care about. And then when it gets to that node in the destination system, then the destination's routing will take care. The routing in there will take care of getting it. Now, the routing doesn't necessarily stay put. It can change based on the congestion in the network. Maybe one of the routers has gone down. All kinds of reasons. And in fact, when you get up to outside of the autonomous network system, It can depend on the fact that one provider doesn't want to pay the price that another provider wants for sending something through its network and wants to use a different provider. Now, we can set the route up ahead of time, a virtual route, and all the datagrams will go that way. That's not the way we do it. Normally what we do is we do circuit switching. Circuit switching means that when I come in to one place in a router, I know which way I go out. But it's not my line. It's not dedicated to me. It is a line that could be used by others. And furthermore, I can't guarantee that every packet I send will go that way. They may go through different routes if congestion changes, for example. So I can't even decide that they arrive in the order they were sent. Now, how do we address things in the internet? We've already done this, but let's go into some detail, more detail maybe. You and I like Euros. www.providence.edu. That's very understanding and easy to remember. But the system, as you should know from what we did earlier, has to convert those to numeric addresses. And the numeric addresses are called the IP addresses. We looked at the system to do that, the protocol to do that, the domain name system. We looked at some of those protocols in Wireshark. Now, originally, back in the Stone Ages, which I think for computers is like for the internet is somewhere around 1980, the IPs were 32-bit addresses. Somehow the people weren't very forward-looking then. They thought that they could get away with 2 to the 32 into different addresses. Well, that did not work. It gave out probably at least by the turn of this century, and maybe before that. They were nice, and the problem is all the routers along the whole network and all the protocols were set up so they had a space for a 32-bit address for the source and a 32-bit address for the destination. They didn't work. There wasn't enough room. So they moved to IPv6 addresses. So now, I don't know what happened to version 5. I think they don't like odd numbers or something. IPv6 really went all the way. It quadrupled the number of addresses. 128 bits for one address. That's a lot. It's supposed to be sufficient. I think it probably will be. Now, what had to happen? Well, all the routers had to change. And there's quite a few routers in this world. And not only that, but the protocol headings had to change. So all the software programs that work with the protocol headings had to change. Well, that wasn't done overnight. In fact, IPv4 addresses are still around. And I believe there are still networks that can't use IPv6 addresses. I don't know how many are left, but they have provisions for those who can't. It's a problem. Now, let's look at what an IPv6 address looks like. What I'm going to do is I'm going to try to bring up the header. That's not what I want. Sorry about that. This is what I want. Is that the right one? Yes. I'm going to move that to that side. And I'm going to bring up what we've been looking at. And I'm going to move that to this side. And that didn't work very well, did it? Let's try that again. All right, that's better. I think I can get it right. All right, leave it where it is. Leave it alone. All right, what I've got here, this is a version 6. I wanted a version 4. I'm sorry. I had a version 4 here somewhere. That's version 6. This is version 4. And this one I can just get rid of for now. And I'll move myself down here. Now it's all within what you can see. On this side is the IPv4 header. On this side is an example of the IPv4 header. The header is 20 bytes at the beginning, and then other things. The payload, I guess I would say, or whatever. If you look at this, the blue part that's highlighted are the actual numbers. Now we can see some of them pretty easily. The first 4 bits are supposed to represent the version number. If you look at the highlighted section, the first half byte, which is the first 4 bits, is 4, and that's the version. The IHL, I'm not sure what that means. I didn't bother looking it up, but it's 5 in our case. And type of service, we don't need to worry about. Total length. I wanted to see if I could figure out if the total length was correct. Up here it says the total length is 337. I computed that to base 2, or base 16, and I looked at what I had down here, where the total length was supposed to be, which are bits, which in this particular case is 0151. And if you look at that, we have 1 plus 80, 5 times 16, plus 1 times 256. 256 plus 80, that one is 128. No, it is 256, pardon me, it is 256. Then I have the 80, that's 336, and the 1 is 337, and sure enough, that's what the length is. So look at 0151. It's on the second line, the first 2 bytes, and you can see that they're not lying to us. That is where the length is. Now further down, in the last 8 bytes that are highlighted in the blue are the source and destination addresses. And the way they were written in those days was that we had 4 numbers in decimal separated by dots. And what those numbers represented was the value that was going to be stored in a byte. So in the destination address, the first number is 70. 70 in base 16 is, well, base 2 first. It's 64 plus 6. 6 is 0, 1, 1, 0. And if you look at the byte, let's see if I can find it. 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's in the second line, the next to last in the blue, the 4, 6 represents the 70. And if you calculate some of the others, you'll get the numbers up there. So you can see that they had just enough room for the IPv4s. That was it. So now you've seen it in the theoretical way and in the actual way over here. I'll put this back down and I'll take this back up. So that's IPv4. Now let's take a look at IPv6. And that's the same thing, just from a different source. Now here's the IPv6. Nobody wants to write that out. In this case, it's in hexadecimal. It's no longer in decimal. And that means each of those zeros and ones and whatever and fives and A's represent 4 bits. So there are 132 bits there. The 4 into 132 is 32. I don't want to put down 32 bits of these. Notice how they do it. They're 1, 2, 3, 4, 5, 6, 7, 8. I think I counted wrong. Basically, we have 8 numbers to represent a IPv6. But since not all of them have something in them, if they are zeros, we can not write them by putting a colon, where the zeros are, we can have colon, colon. And that tells us that those are the things that should be there are zeros. In this case, the last 4 were zeros, so we put the colon, colon at the end. If you go up higher, there's the new header. And of course, I do have one of those. Let's see, I need the V6 one now. And this is the V6. And I'll highlight it. You can see it's bigger right off the bat. And you can see the 60 at the beginning. Remember, the 6 is the version. And then we have payload length. It says 1460 here. If you were to look at those bytes, you'd get 1460. And then in the bottom here, you have the huge addresses that are there. You can see they're pretty big. And if you look at the first address, there's a lot of zeros in it. You can see a lot of 0, 0, 0, zeros. And that's not surprising because if you look up here, you see a colon, colon there. So you could actually figure out what they are. And you can see that they are where they are in the header. That is the header. That's what's put on what comes down from the transport layer. So I'll put that away and put this up again. Now, what do we do if we have to go through somebody who doesn't recognize IPv6s? Well, the method they decided on was something called tunneling. the place where the IPv4 address would be is actually a pointer of some sort to tell the protocol where the IPv6 address is. So it points down to the actual address. But as far as the network is concerned, it can work with the IPv4 addresses. They're arranged in some way so that they can get to the right place. Now let's look at a little bit of the way things are done. This is a virtual circuit setup. This would be at one router, and what it would say is that if you have a record coming from your neighbor A, which is marked as circuit 1 from A, and you would send it out to your neighbor B, marked as circuit number 1. If you got something from C with marker 1, you would send it out to B, but it'd get a 2 as its circuit number because 1's already in use. If you get a second one from A with circuit number 2, then you would send it to C with circuit number 1. This table would be set up before you started sending the messages. Each router along the route would put an entry in its table like this. So when my message from A marked as 1 got to B with a marker as 1, B would look in its table that looks like this and say, all right, where do I send it? Who's my neighbor that gets this and what marker do I put on it? That's a virtual circuit. Packet switching is more likely. And packet switching is a little more complicated. We still have tables. But there is absolutely no way we can have a table with every possible IP address to every other possible IP address. The only way to do this is to have groups. So in this particular setup, we say, if I send you an IP that has 15.6.8.7 as the address, then that is between 15.6.8.0 and 15.6.8.127. So you should send it to X. If I send you one that is 15.6.8.23, it's still in there and you can send it to X. So this way we create groups to send things out on. Saves us lots of room. We know part of it. The rest of it knows part of it. I wrote some of the things that are represented there. And we'll look at that in more detail later because there are some other things we have to worry about. I think I'm going to stop here and we'll pick this up probably tomorrow. See you later now.